Hey everybody, Noah here with Learn Meta-Analysis, and in this video we're going to continue our exploration of running a three-level meta-analysis model using standardized mean difference effect size in Metafor for R. So, if you recall from the previous video, we have already, I'll start in the beginning of the code, we have already uploaded our data file. We've calculated our effect sizes and we've named that into a new data set here, and we have saved that within as a .csv already. So what we're going to do is now we're going to actually run our three-level meta-analysis model, okay? And so importantly, we're not using correlated and hierarchical effects. We are not using robust variance estimation. This is just a typical three-level model. We'll have different videos that show how to do, for example, the correlated and hierarchical effects piece, as well as the robust variance estimation piece. So for now, let's just focus on a standard three-level meta-analysis model. So if you recall, this little arrow fella here is letting us know that over here to the left, we have a name of what we're going to name something, and anything to the right, the result of what's happening to the right, should be named what happens to the left. So here we're going to call this m_multi for multi-level model, and over here on the right, we have rma.mv. That lets it know we want to use a random effects meta-analysis, and we are going to be doing multivariate or MB. So next we jump to here, yi, that's our effect size. That's the same thing it's called in our data set, so we don't have to change it. VI, same thing it's as our data set. We don't have to change it. Next, we get to this random one with a bar. So this structure here is just going to remain the same for three-level meta-analytic models, okay? And then over here on the right, this is pretty important, okay? This is what we really want to pay attention to. So what we are saying with this little piece of code is that our studies are actually called studies and our effect sizes are called effect sizes. So what this is doing is this is setting up a structure where we have effect sizes nested within studies. Okay, so if you think about it like from a top-down perspective, we have our overall analysis at the highmost level, then we have the studies at the medium level, and then at the very bottom, we have our individual effect sizes. So that is the way I like to think about this, is I like to think about it as different levels, so to speak, almost like a cake. So at the very top, I have my overall analysis. Then in the middle, I have my studies. And then at the very bottom, I have the effect sizes within those studies. Method, we're going to use REML, restricted maximum likelihood estimation test. Okay, so this is an important one. So I actually wasn't aware of this until I started reading more about three-level models. So if you read on the metafor documentation, it's recommended that we use a t-distribution rather than some of the others that are available when doing these multi-level variables. You can read about that if you want to, but for the sake of now and not being super statsy, we're just going to say test equals t. We are also going to set our degrees of freedom as contained for similar reasons. And last but not least, we are going to set our data that we're going to be analyzing as DAT1, which if you remember, this is what we called the data with our effect sizes earlier when we actually calculate our effect sizes. Last but not least, we have this call to actually display the data here in our screen. So let's go ahead and we're going to highlight this whole thing. We're going to hit run. All right, wonderful, beautiful. Let me open this up a little bit so that it's a little bit easier for you guys to see. Okay, so here we can see we have our multivariate meta-analysis model. We have 35 comparisons here, and we used REML. So the first thing I like to look at is my model results. So what is the overall effect? As you can see down here, our overall effect was negative, that's interesting, negative 0.378. So I would consider this to be a number one, negative, so our control group did better, which is interesting. Small to moderate effect because we're using standardized mean difference here. When we look over here, I'm next going to look at the p-value. Oh, non-significant. Okay, so we did not actually see significant differences between groups. That's interesting. And then we have some of our other statistics like confidence interval type things. I'm not going to go over those. I'm going to assume that you guys know those. Okay, so next we need to look at heterogeneity. So we're going to look at the test for heterogeneity, and we can see overall we do have some heterogeneity here. It's a statistically significant result for our Q-test. So up here we have these things, sigma 2.1, sigma 2.2. If you are familiar with conventional meta-analysis, these are essentially our tau squared values. So 2.1 is going to be within, this is going to be our between study heterogeneity. and 2.2 is going to be our within study heterogeneity. So you can see here that most of our heterogeneity is coming from between studies rather than within studies. So that's just interesting. It's a good point for us. So we're going to keep that in mind as we continue through here. So the next thing that we want to do is, if you're familiar with meta-analysis, you may want to look at I-squared, right? You're probably thinking, hey, why is no I-squared presented here? I-squared is presented in conventional meta-analysis. Why don't we see it here? Well, what we need to do is I put a link here within our code, and we need to actually teach R how to do the I-squared calculation. So what I'm going to do is I'm just going to open up a new web browser. I'm going to go to this website link, and you can see it's a whole bunch of code. I'm just going to do Control A, Control C, then I'm going to paste that into my console. Note that I said the console. That's down here at the bottom. I am not putting it in my code area. I'm putting it in my console. And then I hit Enter. And now if you see over here on the right, you can see it learned two new things. It learned the MLM variance distribution, and it learned var comp. That's important, okay? So give me just a second here. Okay. All right, so we got that all structured. Sorry, I had too many things open on my other screen, so I was trying to get it minimized so I can focus. We are going to just highlight this code, and we are going to go ahead and hit go. I should probably tell you what this code does. So we're going to name this I2. We're using this new var comp function, and we're using it on our multi-level model that we just set up. Then we are saying we want the summary information from this analysis, and then we are displaying it. And when we run that, we can see two things. One, we get this nice little image over here on the right, which we're going to come back to. And number two, over here on the left, we have the actual information written out. Okay. Okay, so this is quite interesting, isn't it? So if you remember, we had a lot of between study heterogeneity, but not a lot of within study heterogeneity. And that is actually the same thing here. So if you look at this, at level 3 is our between study heterogeneity. Okay, and this is 91.56. When we look at our within study heterogeneity, this is 5.63. So this is consistent with what we were seeing with our tau squared. Okay, so that's the main thing that I'm looking for here. Something that's confusing, and part of the reason why I had these other screens up here is I'm just going to show you this. I'm going to scroll up. We're going to go back to our previous data set. This is what takes me a long. I always forget if I'm not doing this like all the time. I always forget. So here on this first line, between study heterogeneity is presented first in metafor results, right? Then it's within study. But then when we get down into the I-squared, it actually reverses to where we see within study presented first and then between study presented second. And I always just have to double check that and make sure that I'm interpreting that correctly, because unless you do this every day, it's really easy to forget. But that was part of the reason why I had so many different screens open over here, because I just wanted to make sure that I was giving you guys the proper information. So, and I was. And the other thing that we can do is we can check and make sure that what we're seeing is consistent. So like I said before, here we have our between study heterogeneity is 91.56%. That corresponds pretty well to our tau squared value being much larger for between study heterogeneity than within. We also, from this, have our total I-squared, which is our total heterogeneity that we're seeing. I shouldn't say total heterogeneity. It's the total amount of variance here. So what we're seeing between these two levels is simply just an addition of these two things, and we're seeing that that's 97%. So that's very high, right? That's very high. So we know we have some heterogeneity happening here. Okay, so where are we at in our analysis? Next, we are at outliers and influence. And we're going to go ahead and we're going to do this now. I thought about having this as a separate video, but I want to just combine it with this one for the sake of ease. So what we are going to do to check for outliers and influence, the first thing that we are going to do is check for outliers. And we are using Van Liese's method, and I put a link here to where they talk about this. But basically what we are going to be doing is we are going to be looking to see if we have any effect sizes where the confidence interval for that effect size does not at all overlap with the confidence interval from our overall meta-analysis. Okay, so I know that sounds a little bit weird, but if you think about it for a few minutes, it'll make more sense. So we are looking for effect sizes where the confidence interval for that effect size does not at all overlap with the confidence interval for our overall meta-analysis effect size. So we are going to go ahead and we are just going to calculate, we're going to run all of this at once, but I suppose we should run through what some of these pieces of code are. So what we're doing here is we are looking at the upper and lower confidence intervals from our data set. We are also looking at our effect size, and we're doing plus and minus 1.96, and we are taking the square root of this when we do this to compute it, and basically we're just computing what the lower and upper confidence intervals are. Then we're going to create our filter, and we're going to count the number of outliers. Okay, so I'm going to run this piece first. Okay, so what you can see here that I want to show you, this is our data set, right? This is our whole data set all over again. But here at the end, we have a couple new things. We have upper CI as we computed, lower CI as we computed, and then we have this thing called outlier. And this tells us if a particular row or comparison is or is not an outlier by this criteria. Now, I find this a little bit challenging to look at in this format, so I also like to use their code for creating a plot, just because I find it much easier. And if you look over here, you can see that we have a pretty interesting plot where red is actually not outliers, but green is. And you can see we have 3 on the negative side that are considered outliers. So that's all nice as well. So I like to actually make this into a CSV file as well, so that way I have this saved for later. So that's what this next piece of code is doing. So I'm going to go ahead and just run that, so that way it's saved my outlier code. Okay, so to kind of rehash what we just did, we computed some new confidence intervals. Then we looked to see if every single comparison had a confidence interval that overlapped with the meta-analytic overall confidence interval. And what you can see is that we ended up with 3 potential outliers. Now, if we were actually running this as a meta-analysis, at this point I would stop and I would take a few minutes and I would go back and I would look at this particular data. First and foremost, I would look and see if I have any typos, particularly with something like this, all the way out here at -8. That's kind of crazy, right? So I'd go look and see if I have any typos. I know for a fact I didn't in this data set because this is a small sample of a larger meta-analysis that I did. So I know that I didn't actually have any typos in this. So the next thing I would do is then do my influence analysis. So I have a link here where you can read about influence diagnostics, but the first thing that we are going to do is calculate Cook's distance. And here we're looking for a value over 0.5, okay? So what we're going to do is we're going to say we want to calculate the Cook's distance based off of our meta-analysis model, and we're going to call it Cook's. Then we are going to plot it. So let's highlight these and run that. Okay, so over here on the plot, you can see on the left-hand side, our Cook's distance doesn't get anywhere near 0.5. Right, the highest value we have is like 1.6 or so. I'm sorry, 0.16 or so. Maybe not even that high. So we don't have any significant influence judging by Cook's distance. Now let's look at DF betas. And with DF betas, we're going to be looking for values over 1 to see if we have any influential comparisons. So here we're doing DF betas based on our meta-analysis model, and we're going to call this DF betas, and then we are going to just display the data. Okay, so you can see it came up here in our console, and we are looking for a value over 1, and this should be like an absolute value. I should have put that in here. Okay, save that. Absolute value over 1. So basically we're just looking at the left side of this decimal point here, and you can see we actually don't have any. So last but not least, we are going to calculate hat values, which is just another statistic that we can use to look at influence. Here we're doing a little bit of math to figure out what values we should look at, and I put a note here that I got from the metafor documentation. So we're looking for values larger than 3 times p over k, where p is the number of model coefficients and k is the number of cases. Okay, so that's what we would do, and that's a little bit hard to do. Like, I'm not doing that mental math, right? Like that's more math than I want to do in my head. So what I do next is I actually export all of this over into an Excel file. And so what I'm going to do here is I'm going to tell R that I'm going to create a new thing called influence, and then I'm going to bind these columns together. And the columns in my new table are going to be the Cook's distance, the DF betas, and the hat values. And then I'm going to write all of this to a CSV file, and I'm going to call this CSV file influence info. So I'm going to go ahead and I'm going to run that. Now, as you can see, R says, hey, buddy, I did that. And then down here it says, hey, I also made this file for you. Okay, so if I was doing this for real, what I would do next is I would go into my CSV file that I just created, and I would create a filter where I'm doing this math, the 3 times p over k, and I would first compute this value, and then I would have it indicate to me if there were any hat values that exceeded that. From what I recall, there aren't any in this particular data set. Let me check that and see if I have a note about it. Give me 1 second. Just skimming through. This is the same example, by the way, that's in my open book. So if you have trouble following along with the video, there's a link to the description where you can find this chapter. Okay, so I said the same thing there. So I said, okay, for the sake of our conversation, we're going to pretend like we didn't find anything that's influential. So while we're here, let's talk about a reality of this whole thing, okay? Let's talk about a reality of what is an outlier, what is influence, how do we deal with these things? First of all, I've seen a bunch of different ways you can look for outliers. Then I've seen a bunch of different ways that you can look for influence. Then I've seen a bunch of different ways that talks about what is an outlier, isn't an outlier, what do you do with it? So my current opinion as of September 2024 is, I'll tell you what my opinion would be with this data set. So with this data set, we had 3 outliers, but none of them were influential. Assuming that there were no typos, I would leave those outliers as they are. And the reason is that I would consider it to be valid data. If I went and I looked, I didn't see any typos in my data. When I looked at the methods of the study itself seemed sound. It seemed like a valid study. They didn't do anything notably different than the other studies in my sample. And those particular outliers were not significantly influential in my overall meta-analysis result. So based on that, I would leave those studies as is. Now, I have not run into a situation where studies are outliers and influential and it's a bad study. I haven't had that particular situation yet, so I'm not really sure what I would do in that situation. I have had the situation where studies are outliers and they are significantly influential. However, when I go back and I look at that study, there's usually a reason why it's significantly influential. So as an example, maybe there is a huge sample size for that study, so it's getting more weight. And in that case, I would probably, it depends on what you're looking at and everything, but I would probably be inclined to leave it as it is, because if it's a valid study and it's consistent with everything else in your data set, then I don't really see a reason to change it. But it's a lot really depends on the context and what the implications are for your actual results. So keep all those things in mind. I like to think of outliers and influence analysis as additional contextual information that helps support what I'm doing in my analysis and what I'm claiming from my analysis. So that's the way I like to think about influence and outliers. I don't necessarily like to think about it as like one particular thing means I have to do something as a result. The only thing that I ever have to do if I get significant results here is go back and look and see and try and understand, why might this be significant? Is there a typo? Did this study do something completely out of the box compared to all the other studies in my analysis? So I have a separate video on outliers and influence where we talk about these things in a little bit more depth. So I'm not going to ramble on too much about it here because I have a bad tendency to ramble about things. But anyway, that pretty much gets us all the way through. We did our meta-analysis. We examined outliers and influence. We had some outliers, but no significant influence. So we're going to leave our meta-analysis as is. We also looked at the sources of variance in our sample, calculating our I-squared. So in our next video, we're going to look at the categorical moderator variables. So thank you guys a bunch. I hope this was helpful, and I'll see y'all in the next video.